Now, short review for calculating inverse functions. If you have the graph or a table of x and y, you can just interchange the x and y axis or interchange x and y in the table. So if you have y equal f of x, you can write it down and then interchange x and y in the equation and solve for y, and the y that you solve for is the inverse function of x. Now, let's consider what the derivative of an inverse function might be, if indeed the function itself is differentiable. Now, we're going to take a very simple case and get an idea of what its inverse might be. First of all, let's take a function y equal 1/2 x plus 1. Obviously, the slope of this function is 1/2, and if you take the derivative of f of x, it's d dx of 1/2 x plus 1, which is just 1/2. Now, we claim that the inverse function can be written as 2x minus 2. Let's follow the procedure for how we would show that that is indeed the inverse function. We write down first y equal 1/2 x plus 1. If we want to find its inverse, we interchange x and y, get x equal 1/2 y plus 1 after you interchange x and y. And solving for y, we would now say that 1/2 y is equal to x minus 1, subtracting 1 from each side, and now multiply by 2, and 2 times 1/2 y equal 2 x minus 2. And that shows that y is equal to 2x minus 2, and so indeed the inverse function is equal to 2x minus 2. And look, the derivative of the inverse function, which is d dx of 2x minus 2, is 2, and the thing we notice is that in this case, the derivative of the inverse function is a reciprocal of the derivative of the function itself. Now we're going to see that this is true in general. By the way, here is just a graph of, first of all, the original function y equal 1/2 x plus 1 with a slope of 1/2, and in yellow here is the graph of y equal 2x minus 2, and you can see that its slope is 2, and therefore the reciprocal of the slope of the original function. Now let's look in general, and we're going to show that if you pick any given point, like A and B, on an original function, you can imagine the slope of the tangent line, and I've drawn it here as a tangent line. And as you know, if you draw this line and then look at the rise over the run, which would be the change in y divided by the change in x, that would be dy dx at the point A and B. It's equal to delta y divided by delta x. Now, next we're going to draw the graph of the inverse function of what you see here. And what we're going to do is this is going to become the y-axis. We're going to interchange x and y. That's going to become the x-axis. And then we're going to flip everything around so that the old x-axis is pointing in the y direction, and the old x-axis, the old y-axis is pointing in the x direction. And we're going to see what it looks like. As you can see, it's the same curve, except it's flipped in the other direction. This is what we mean by interchanging x and y. And now we originally had the point A and B on the original function. We now want to look at the point B and A. That's the interchange values of x and y at the point A and B. Notice that the tangent line is still going to be drawn on the original curve like it was, but now in this new orientation, the slope of the tangent line will be delta y divided by delta x. Now, this is exactly the reciprocal of the slope of the original function. So now we can say that dy dx of the inverse function at the point B and A is equal to del x over del y on the original graph. In other words, the derivative of the inverse function at B and A is the reciprocal 1 over d dx of f, the original function, at A and B. Therefore, the derivatives are reciprocals of each other. Now we're going to work a couple of simple examples to illustrate this. So example here is to take the equation y equal x squared for x more than 0, and we're going to use the value of the derivative at the point 2 and 4 to calculate the derivative of the inverse function at the corresponding point 4 and 2 without calculating the inverse. So now y is equal to x squared, so dy dx is equal to 2x, and at the point x equal 2 is equal to 4. So without calculating anything, we know that ddx of the inverse function of x is going to be the reciprocal 1/4 at the point 4 and 2. See how simple that is? If you look at the next page, we have the original function y equal x squared. It's pretty obvious that the inverse function is going to be the square root of x, although we didn't really have to calculate it. The square root of x function is given here in yellow. And as you can see, if you go at the point 2 and 4, the slope of the tangent line is 4. If you look at the point 4 and 2, the slope of the tangent line is 1/4. Now let's work one last example. Let's take the function y equal x cubed minus 2. We want to take the value of the derivative at 2 and 6 and calculate the value of the derivative of the inverse at the point 6 and 2 without calculating the inverse. So let's take dy dx is equal to 3x squared. And we'll look at point x equal 2. That's equal to 12. So without doing any more calculations except taking the reciprocal, we know that d dx of the inverse function of x is going to be 1/12. And indeed, on the next, you can see the original function, y equals x cubed minus 2. The inverse function is plotted just by inverting the x and y values and plotting it, and you can see at the point 2 and 6, where the slope is 12, at the point 6 and 2, the slope is now 1/12. Now, we're going to go back into college algebra a little bit and review what a logarithm is and some of the properties of logarithms which we need to know. You recall that we talk about the logarithm of x with respect to the base b, where b is the base. When we say y equal log of x to the base b, it means that x can be written as b to the power y. Now, let's just take a simple example. Suppose we wanted to take the log of 100 to the base 10. We need to figure out what exponent we can raise 10 to get 100. Well, in this case, it's going to be 2. So the log of 100 to the base 10 is equal to 2. You might go back and review some of this so you'll understand logarithmic functions when we cover them. Now, there's another important formula that tells you how to easily calculate the log of x to any base if you only have available to you the ln function. And it says the log of x to any base b. It's just simply ln of x divided by ln of b, the base you want to take the logarithm with respect to. So if you wanted to take log of 50 to the base 6, you would just take ln of 50 on your calculator and divide by ln of 6. Now, 3 more properties of logarithms that are very important. The logarithm of a product, x times y, is simply the logarithm of x to the base b plus the logarithm of y to the base b. The logarithm of a quotient, log to the base b of x divided by y, is going to be the log of x to the base b minus the log of y to the base b. And then finally, log of x to the n to the base b is going to be n log of x to the base b. Now we're going to use these properties in other places in this course, as you will see.